section in this chapter, this introductory chapter, and we're going to talk about quadrics. The goal of this section is to go through a couple of important three-dimensional objects that will, as I mentioned before, will be used to illustrate the most important concepts in Calculus 3. When I teach this section, I kind of redesigned the way I cover this along the years after I taught this class repeatedly. I used to spend more time that I'm going to spend today. I think, spend more time than the average professor on this section. It's not it can be a time-consuming section if you actually want to go through every detail, so to speak. But I don't think it's necessary. I think we can strike a balance between the two. So the point is this notion of a quadric. This is basically a class of three-dimensional objects with certain properties. We'll get to that in a minute. But instead of going over every single detail, I'm going to focus primarily on the quadrics that will be used most often, because when you go through the class, you will realize later that some of the quadrics mentioned in this section are not actually used that often. But we should just mention them at least once. Furthermore, we're going to rely a lot on computer algebra systems such as Maple or similar. By the way, this presentation is going to end with the part that it's done again on Maple, so a little bit of a demonstration. Because by hand it's very hard to draw an accurate sketch. You should still have the ability to actually sketch just briefly or schematically the most important quadrics in the problem, just enough to actually set up an integral, for example. But more details than that, you rely on computer algebra systems. And furthermore, the equations of quadrics will be gathered in some sort of a formula sheet, which I will present. It's actually, you can just basically have a copy from a book. Most calculus books will have basically a cheat sheet, if you want, with these most important quadrics. Well, let's actually start with the basics to see what they are and what are their most important properties. Before we define what a quadric is, let's actually review briefly three important two-dimensional objects, also named as conics. So I'm talking about a parabola, an ellipse, and a hyperbola. Now, there are general equations of these, but to maintain simplicity, we're going to talk about these figures when they go through the origin. So either they go through the origin or they have the origin as a center of symmetry. For the parabola, we're going to talk about the one that goes along the y-axis. So for the parabola, let's take a look at the equation y equals x squared. Right, so this is the simplest parabola probably that you encountered in Calculus 1, let's say, going to the origin. Again, with translations, you can, of course, have this parabola on a different position, like with the vertex on a different position. You can have it tilted. Another version, for example, if you interchange x with y, obviously that gives you a horizontal parabola, the way I like to call it, right? I mean, for which the x is the axis of symmetry. And the ellipse, this one with the center at the origin, as I mentioned before. In fact, here's another little trick. Let's actually sketch the ellipse and the hyperbola in the same coordinate system, because they are somewhat related. And so the ellipse has the equation, I should have left room here for it, what the ellipse will have the general equation x squared over a squared plus y squared over b squared equals 1. And the hyperbola will have the equation x squared over a squared minus y squared over b squared equals 1. So if you sketch the rectangle with sides with the intercepts A and B for the X and Y axis, like that, I mean, it turns out that the ellipse actually is the closed curve inscribed in this rectangle. And if you sketch the diagonals, the hyperbola, which is made of two pieces, asymptotic to these diagonals, are like this, right? So, in fact, let's actually use a different color just to distinguish the two. So the red one is the ellipse, and let's say the green one is my hyperbola. So I mentioned this because the quadrics we're going to talk about are named according to whether intersections between them and horizontal or vertical planes are either parabolas, ellipses, or hyperbolas. So the quadrics we're talking about are a class of three-dimensional objects for which intersections with horizontal or vertical planes will give you one of these three curves. That justifies the naming of these shapes. So here's one type of surface, and what's important, I should mention here, it's extremely important to visualize what goes on when you have an object described by various equations. Now you have to, of course, know the formula for some of these equations. I mean, for some of these objects, you need to know what they are. But try to visualize as if, for example, you knew nothing about the shape of it and you try to discover it by trying to figure out the properties of the coordinates. So, for example, what if I say, well, actually, let's actually define first of all what a quadric in the general sense is, and then we'll go through the list. So, a quadric is any three-dimensional surface whose equation is given by a linear combination of x squared, y squared, z squared, xy, yz, zx, x, y, and z. So linear combination up to degree 2 for all of these variables, for the coordinates. So it's a pretty general definition, obviously, right? So like I said, let's start with our important list relevant for our class. So the first one, it's a so-called cylindrical surface. Sometimes it's called a cylinder, but this term is kind of misleading because most people will associate the cylinder with the straight cylinder whose cross-section basically is it's a circle. But this is a more general concept. So, and we talked about a little bit how you figure out the way these equations look like. So what if I say to you, describe in R3, right? I mean in the three-dimensional space, the equation of the surface given by, the surface given by the equation y equals x squared. Now remember, pause for a moment and remember what I told you. What can we say about, what can we conclude, what can you infer if one of the coordinates is missing in the description of the equation? And so remember, that means that variable, that coordinate takes any real value. So that means z really takes any real value. Now, just in terms of x and y, this describes a parabola, right? So if I were to sketch this to try to figure out how this looks like, our coordinate system, right? Let's say we stick to z equals 0 as an example, right? Z takes any value, right? But let's situate ourselves on the xy plane. Now, obviously, this describes a parabola, which is along the y-axis, right? So with the y-axis as the axis of symmetry. Okay, but as z varies, like for example, let's say this is for z equals 0, right? But let's say z equals 1. X and y still describe the same motion on a parabola. So now you have a parabola localized on an upper plane here on z equals 1. And you can imagine what goes on, right? I mean, if I pick another value for z, x and y describe again another surface, another parabola. So as you imagine that z describes, goes to all the possible real values, you kind of see hopefully that you obtain what we call here a cylindrical surface, right? In the sense that it's like a cylinder, but with a cross section, even by a parabola, horizontal section. Okay. And this leads me to one important definition or a way to describe a picture, or three-dimensional picture, via the so-called tracing method. So for instance, you have a three-dimensional object, you cut it with horizontal or vertical planes, and you vary these planes, and you look at the intersection between these planes and the surface, and you basically have an idea of how the overall shape of the object looks like. Another important application of this trace exercise, figuring out how the trace looks like, is because many objects that we're going to deal with are combinations of other objects. Like they will say, for instance, take an ellipsoid, cut it with a plane, at z equals 5, and another vertical plane at x equals 2 or something like that. So you need to know how these shapes intersect, because that intersection is going to play an important role, a crucial role in fact, when you set up the tool you need to use. For example, setting up an integral to find the volume, or a surface integral, whatever the case may be. All right, so let's move on with the next page and continue the discussion. All right, so the next class of quadrics are the hyperboloids. We're not going to use them too often, but we're going to mention them, and I'll show you how they look like on Maple. So there's two of them, two types. The hyperboloid with one sheet. That means it's made of one piece only, and its equation is x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. So the way you sketch it, again, let's talk about the traces first, and then we're going to talk about how we sketch it. Horizontal trace, again, that means intersection with a horizontal plane. Let's say z equals k. Imagine again you plug in an actual number into the equation of the hyperboloid, and then see what you get in terms of x and y. Right, so all of this is going to be again a real number. It's a positive real number actually. So obviously with what you have on the left side, you should recognize that this is the equation of an ellipse. Okay, so a horizontal trace, and it's going to be an ellipse. What about a vertical trace, which by the way gives the name of these quadrics, right? So I mean the vertical trace whose equation is going to be, let's say it can be either over x-axis or over the y-axis. Okay, so let's say I do it over the y-axis. Okay, so a vertical plane perpendicular, a plane perpendicular to the y-axis. Again, if I put it back into the equation of the hyperboloid, move the terms around, k squared over b squared comes on the right hand side. Again, this is going to be a real number. In terms of x and z, this is going to be a hyperbola. It's important to realize that it's not obligatory that these traces exist for every value of y. I'll get to that in a moment, because that's what makes, for instance, hyperboloids of two types with two sheets or one sheet. For example, a horizontal trace will exist for any number z. I mean, if you look here, when I plugged in a number for z, you can plug in any real number, right? Because k squared over c squared plus 1, no matter what the value of k is, whether it's positive or negative, right? So any real number will make this quantity positive, which is in complete agreement with the left side, which is also positive. On the other hand, and now comes with the other type of hyperboloid, the hyperboloid with two sheets. That one, the equation has two negatives and one positive. And in this case, if you look carefully, and we should do that with an example, maybe. If you look carefully, I cannot actually plug in all possible values for z, right? If I look at a horizontal trace, for example, like before, if I plug in z equals k, clearly the right hand side, which should be negative, right? Because on the left I have only negative numbers, it's only negative for certain values of z, right? So this should be negative for the expression to make sense, right? Because on the left side you have a negative quantity, so minus z squared plus c squared, minus z squared over c squared plus 1 should be less than 0. That's another way of saying that z squared over c squared should be greater than 1, which is another way of saying, if you solve the inequality, z should be greater than c, or z should be less than minus c, assuming that c is a positive number, of course. So that means there is a gap in the picture between minus c and c, right, for z. So when you sketch them, the hyperboloid with one sheet looks like this. Let me actually just forget about the coordinate system, right? Looks like this, right? I mean, or maybe we should sketch it just briefly. Sometimes the coordinates of the system, I mean, interfere with the visualization if you do it by hand like that, okay? But this is roughly how the hyperboloid with one sheet looks like. Right here, it's the ellipse, the smallest ellipse, right, when you intersect it with the plane z equals 0. Z equals 0 corresponds to the narrowest part of the hyperboloid. I'm going to mention some interesting properties of hyperboloids. In practice, they can actually be generated by straight lines. We'll get to that in the last part of the class. So this is the one whose equation is this, right? The hyperboloid with one sheet. And the other one, like I said, it has a gap between minus c and c. And it has two pieces, as the name implies. Kind of like that. Again, if you take notes, don't go overboard with this. Most of the time, we're not gonna need to do this on paper. Basically, we're gonna stick primarily to ellipsoids or paraboloids, elliptic paraboloids that you'll see in a minute, because these are usually easier to sketch and manipulate. So, right, okay, let's move on with the next page. The last quadrant I want to mention is the so-called paraboloid, right? The elliptic and the hyperbolic one. Hyperbolic paraboloid is usually the hardest one to sketch. I'm not going to even attempt it. I'll just, well, maybe a little bit, and then I'll move on to the presentation with Maple in a minute. After we're going to go over some other exercise or example. All right, so the next example is the elliptic paraboloid. And let's see. The general equation will be z over c, the way it's given in our book at least, x over a equals x over a squared plus y squared over b squared. I forgot to mention this important remark. I mentioned it verbally, but let's actually write it down to make it clear. And we'll get to that. All these examples have a z-axis as the axis of symmetry. So they are along the z-axis. If you interchange x, y, and z, you have, of course, symmetry with the other axis. But we're not going to mention, of course, all three versions of these equations, because then it's going to be too much of a mess, obviously, right? So I'll show you an example in a minute. So you should basically be able to recognize what goes on if, let's say, you have x instead of z and then z and y, like, for example, x on the left, z and y on the right-hand side. Okay, so it'll be the same shape, but along the x-axis instead of the z-axis. So all of these are along the z-axis. So the rough figure of it looks like this. Okay, traces, the horizontal traces, and at this point you should figure out them yourself, I mean, what the shape of each trace is. Sorry, this is kind of a mess here. So the horizontal trace, that is when z equals k, you want to fix z equals k, obviously it's an ellipse. A vertical trace, when you cut it with a vertical plane, like for example, let's say you have x equal to a fixed number, right? That's going to be a parabola. Let's put a quick example here to make it clear what we're talking about. So let's say you have a paraboloid of equation z equals x squared plus y squared over 4. Now, what is the vertical trace? That is to say, what is the intersection of this paraboloid with the vertical plane x equals 1, right? So taken together as a system, that gives you z equals 1 plus y squared over 4. So obviously this is a parabola in z and y, translated a little bit, right? I mean, it doesn't go through the origin, right? I mean, if you look at the, it's going to be, if one is here, it's going to be cut like that, right? Roughly speaking, right? From the paraboloid. You really have to visualize this, what goes on if you slice it vertically, right? I mean, you're going to end up with an infinite parabola, but with respect to z and y. So in other words, if I cut this, if I project this cut into the yz plane, you're going to get exactly the equation of this parabola. Okay. Right. So now let's see the next example, the next type of like I said, the more complicated shape, the hyperbolic paraboloid. When I learned this for the first time, long time ago, this confused me a lot of time when I often when I looked at how the Maple or the computer algebra system generates this this picture. And I'll talk about when we run the examples in a minute. So z over c, that's the equation, equals x squared over a squared minus y squared over b squared, right? So this is going to be with minus between them. The name already implies what goes on, right? So a horizontal trace for this is going to be, like, again, that happens when z is fixed at a number k. Obviously, this is going to be an ellipse, excuse me, a hyperbola. So horizontal traces are hyperbolas. And the vertical trace that is when you fix again, one of these x or y, the vertical trace will be a parabola. From our perspective, is a parabola up and down, if you think about. So here's an example. Let's say I want to sketch, let's say z equals x squared minus y squared over 4. And let's look at, let's see, I'm going to sketch it here. Let's say this is x and y and this is z. So let's say we look at the vertical trace y equals 0. That's going to be, well, let's say, yeah, I mean, one of them is up and up, or the other one up and down, right? Let's say I'm looking at x equals 0. At x equals 0, this vertical trace gives me the parabola z equals y squared minus y squared over 4. So if I look at the plane made by z and y, that's going to be up and down with respect to the y-axis. Like that. On the other hand, if you look at the trace y equals 0, that gives me z equals x squared. So that means in the z equals, in the zx plane, that's going to be a parabola opened up. So this is going to look like a saddle, basically. If you sketch these parabolas along the one that goes down like this, this will resemble more or less a saddle. But again, on paper here, that's not going to be too easy to actually sketch. So I'm not going to even attempt it. So I'll show you with Maple when we run the examples later on. I mean, like last part of the of this lesson. But before we do that Maple presentation, let's actually do one other example that I want to go through that kind of combines some of the stuff we dealt with up until this point, and then we'll finish up with some with a Maple presentation. So stay tuned. All right, so let's go over a quick exercise. Okay, what type of surface is this equation represents? The minus x squared plus 4y squared minus z squared equals 4. So here's the trick here, and remember what I told you before, that all the formulas, all of these equations given in the formula sheet as well, are for these pictures along the z-axis. You look carefully at the power of x, y, and z. Okay, so you look at the equations that contain just x squared, y squared, and z squared, and there is another constant here on the right. And then after a quick inspection, you realize that the only equation in that table of Quadrics that resembles this, okay, so two negatives and both, I mean, like two negatives and one positive in just x squared, y squared, and z squared. The only one that resembles this is the one that I gave you in that form. In this form, minus x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. You may say, hold on a second, I mean, this looks quite different. First of all, there's no 1 on the right hand side, but remember, we can always manipulate it algebraically. So we can easily divide by 4 and then make it in the standard form to resemble the table if we really want to. And then you're going to say, well, but the table states, and by the way, in the table, this is the hyperboloid with 2 sheets. And in the table, that's the equation of the hyperboloid with 2 sheets, symmetric with respect to the z-axis. Okay, so along the z-axis. In my equation, the role of z is interchanged with the role of y. Does that make sense? I mean, think about for a moment, okay? So we have the same type of equation, but with z playing the, like y replacing z. So that's going to be essentially a hyperboloid with 2 sheets along the y-axis. It's two sheets because, again, if I move y to the right hand side, y squared, the the expression y minus 1 minus y squared should be negative because the left side remains negative, which means y squared should be greater than 1. That's another way of saying y is less than 1, minus 1, or greater than 1, which means that when I sketch this hyperboloid, there is a gap here along the y-axis, right? And the two sheets are open like that, right? And these are, for example, the cross sections, right, or the horizontal traces, which are ellipses. Let's do another example. Here's finally kind of like the motivation for doing all of these things. I mean, like, why would we bother? There are problems in which, for example, they could say, you know, find the volume. We could actually figure this out. I mean, it's one of the problems that we could solve by the end of this class. Find the volume of the you know, object bounded by the following surfaces, and then you have a bunch of equations: x squared plus y squared minus z squared equals 4, x squared plus y squared equals 2, and then z between 1 and 5. So as you can see, the description of a three-dimensional object could be a little bit more involved, okay? But remember, you always look at it as a system, and you try to visualize each surface at a time and see how they actually interact with each other to actually figure out the appearance of the object. The first one, you should recognize it as a hyperboloid with one sheet. The second one, you should look at it, I mean, you should recognize it as a cylinder, infinite cylinder, right? Because z can take any value. This region here is the region, this inequality describes the region between two horizontal planes. So these two surfaces, these two quadrics, are cut by two horizontal planes. And by the way, these quadrics, the way are given, are going to be symmetrical. They are along the z-axis, right? Now, what's the narrow part of the hyperboloid? Well, that's going to be when z equals 0, right? Because if you look at the horizontal trace, when you fix z, the smallest value here is when z equals 0. So the narrowest intersection, or the narrowest trace, horizontal trace, is it's actually a circle in this case, x squared plus y squared equals 4. Usually it's an ellipse, right? But in this case it's an actual circle. Horizontal trace for a cylinder is going to be a circle of radius square root of 2. So that tells me that the cylinder is actually inside the hyperboloid. All right, so that tells me quite enough to actually give a rough sketch, which is most of the time all you need. So let's start with the kind of like let me see. Let's start with the hyperboloid. See if I can do that to the best of my abilities. Narrowest part again at 2 and minus 2. Root 2 somewhere in between. And that corresponds to the actual cylinder. So we can look at some sections here, like that, right? Maybe another one up here. And of course, bounded by those planes, obviously, there's a top corresponding to z equals 1. Yeah, I mean, I made this cut here below the x-axis, right? But actually it's z equals 1, z equals 5. So there's another one here on the top, right? The other portion here, somewhere here, that's going to be z equals 5. So I know it's going to look like a mess. There's no way around it. I mean, if you do it roughly like that with the actual sorry, I cut the recording by mistake. So whenever you do a rough sketch in Calculus 3, you end up making a mess. That's kind of unavoidable. But let me I wanted to change the color a little bit. So basically the portion described by this problem is somewhere up here, right, between z equals 1 and 5, right? So it's going to be like a tiny portion here. And you make it like that with the red color, right? So the lower level z equals 1, upper level here z equals 5, right? And then another important thing to realize is that there's a hollow part, right? Because the object is defined by these surfaces one inside the other, right? So there's a hollow part like that, given by that cylinder. So that's the hollow part. I'll show you this with Maple, and it will be hopefully easier to visualize. Those of you who take the class with me, just relax, because usually I'm not going to put stuff like that on written exams. I actually deal with much easier pictures to sketch, okay? But this is to have an idea, because even if you use Maple, you're still responsible to visualize and pick up the correct coordinates. The computation of the coordinates or the intersection points mostly is done or still on paper. And even if Maple actually shows you the picture, you still have to visualize it in your mind. To make sure that actually you set up the integral correctly. And with that, the written part is over, and let's continue with a Maple presentation. And that'll be it for this section. Stay tuned.